not in tangent to M for a general M, in general. So if I start with X and Y in some tangent to a manifold, and I do this computation, the result is not tangent to the manifold, the result is not a vector. And this is why this by itself cannot be sufficient to our derivative here. Okay? Okay, so how we do the derivative? So this is our, what, 9? Maybe? 9 or 10? Anybody keep counting? In our words, the language? 9? I guess so. Covariant derivative, a new word. Remember we started with the manifold? Kept counting, now we're word number 9. Covariant derivative, so given two vector fields X and Y that are tangent to a manifold M, the covariant derivative of Y along X. This is we're going to denote it by nabla x, y. I'm differentiating y with respect to x. This has this meaning. Is the derivative of y along x, is the derivative of y with respect to x, is the derivative of y along or in the direction of x. In differential geometry, we denote it by this symbol. Nabla subscript x to the thing that you're differentiating. Okay? That's fine, but how can I compute it? At the end of the day, I start with two vectors. I need a vector, right? How can I compute it? Well, here is the formula. In coordinates of M. So maybe x1 up to xn, okay? So if I'm on the sphere, I will not do this computation in the ambient space, 3-dimensional. If I'm on the sphere, I will do it in the coordinates of the sphere, maybe phi and theta. Maybe the projection xy. Any two coordinates representing your sphere. Okay? If I'm on coordinates, well, here's the formula, it's not a big deal. So nabla xy, this is a vector, so it has n components. I'll give you the kth component. And you apply it for k equal 1 to n, you got your vector. Is equal to partial yk, this is the kth element of y, partial all your x's plus, let me do it a bit more detailed. Summation j equal 1 to n partial yk partial xj little x, the coordinate, times your large xj plus summation I1 to n gamma ijk. These are functions of x. We're going to talk about in a moment. xi, yj. That's fine. Make complicated, not complicated, I don't care. Here is a formula that allows you to compute your derivative. You're given large x's, the components of your vector field x as a function of little x's. You're given large y's, the components of your y vector field as a function of little x's. Everything is a function of the coordinates, little x's. I'm given this. Somebody magically give me this gamma. I will know how to compute the result. If you look at it, actually, you will find the following. That nabla xy in general as a vector, this guy, if you look at it, it's nothing but partial y, partial little x's as a Jacobian times your x. It's the first thing here. But it's not the whole thing, because we know this is not sufficient by itself. So it seems that this second term is to make up for this. Is to make the result tangent to m. This by itself is not tangent to m. How I can write this is a neat way? Well, this is a vector in the components. I'll give you the kth component of it. The kth components that you put your x's as a row. Gamma, this is a matrix. Gamma ij is a matrix. Y. Multiply a row matrix times a column. The result is what? Row matrix times a column. The result is what? Scalar number or single element. This is the kth element because I have more than one matrix gamma. I have gamma for each coordinate. We're going to talk about it in a minute. So if I'm at the first coordinate, I'm going to use the first matrix gamma 1, the second coordinate is gamma 2, and so on and so on. So this is how I compute the derivative of vector along gamma. So computation-wise, because this is what you may care of for the moment, finals next week, and you have a homework problem due Friday related to this stuff. If you're given a vector x and a vector y, and somebody magically give you these n matrices, will you be able to compute the result or not? Anybody has a problem to compute the resulting vector? Because this is a homework problem. You're given x and y, large x and large y, and you're given these matrices, gamma 1 up to gamma. It's not large, it's gamma 1 and gamma 2. They are 2 by 2 system. And you need to compute the result. So, as you can see, these gammas completely determine how you would make differentiation along a manifold. Okay? So if anybody give you his or her own gamma, it tells you a way of defining derivatives along a manifold. Given gammas, it completely dictates how you differentiate. If you give me another set of gammas, it changes the way I differentiate, right? Because it will change the result of the derivative.
What do the gammas represent in this case?
Okay, so let me talk a little bit. There are no physical meaning for gammas. They are called Christoffel symbols. And so we have their n, like you see, k runs from 1 to n, your coordinates. So they are n square matrices, and they are not symmetric. So as an example, our example on a sphere for, okay? I'll give you the gammas, and later on we'll know how to get the gammas for the sphere. For the sphere, we have our configuration manifold as a sphere. So our little q's, it depends on your little q's. My q's are theta and phi. Okay, so for each coordinate, it corresponds to one gamma. So actually, gamma theta, here is the matrix. I guess this is negative tan phi, negative tan phi. It does not have to be symmetric, okay? Gamma phi is sine phi, cosine phi. Okay? So these are given for the moment. These are given. For any manifold, I can give you actually more than one set of gammas. So given a manifold, given set of gammas, now you know completely how to do derivatives on that band, how to differentiate a vector field. Given gammas, completely tell you how to differentiate a vector field. In particular, if x and y are vector fields on S2, then the covariant derivative of y along x, I'm differentiating y. This is the main difference between this guy and the Lie bracket. The Lie bracket, you differentiate both vector fields. Partial 1, partial x times the other, minus the other way around. You differentiate both vector fields. Here, no. We're differentiating only y with respect to x. Okay? But the result has to be a tangent vector. So this is simply you go and differentiate your y with respect to all the coordinates, x's or q's or whatever, right? Times your x plus this guy is 2 element. Okay? This guy is 2 element. The first element is simply the two components of x times gamma theta times y. The result is a scalar in the first element, and here is the second element. Little x, or large x, I'm sorry, gamma phi times y. So give me any two x and y, any pair of vector fields, I can differentiate one with respect to the other, that's fine. Any question about that? Yes, please.
I have a question about the gamma. What does the gamma depend on? Does it depend on the shape of the manifold in the vicinity?
Oh yeah, exactly, sure.
Okay.
Sure. We will see how to, for given a manifold, we'll see how to get to derive its own gammas.
But you just said you can give more than one gamma,
Yeah.
sets of gamma for a sphere. So,
As long as they abide by the rules. What are the rules is that the result of this process is tangent to the. So as you see, what are gammas here? Gammas are nothing but function matrices, right? And they are allowed to be smooth functions of the coordinates, tan phi, sin phi, cosine phi. Compose them the way you like, okay, in general. Compose them the way you like, such that the result here has to be tangent to the manifold. So to do this, this is not easy. We will see one way of doing it. And as you can see, gammas are functions of the coordinates. So they have to transform from one coordinate to another. There is a way of transforming them. We'll not go deeply in transforming gammas, but we will see how to get them, at least. Okay, I think now we are ready. Ready for what? I told you how to differentiate a vector with respect to another. So in particular, what is the derivative? So given a curve, gamma on M. This means that gamma is x1 up to xn, right, of t. Given a curve and a vector field y, what is the derivative of y along the curve? What's that? Can you give me a symbol for that? Nabla. Let's start by nabla. I like the start. Okay, nabla. Then it needs two stuff here.
The gamma's on the bottom and the y's on.
Very good. So the y here, I'm differentiating y, so I have to put y here. What should we put here? Gamma. Do you agree with gamma? With the definition of nabla, nabla takes what? Two vector fields. Two vectors. We need vectors. This is a vector, and I need a vector here. What do you suggest?
Y gamma?
I need a vector that I'm differentiating with respect to, or along, differentiating along.
gamma.
I mean, we're very tempted to write gamma because we're differentiating along gamma, but I need a vector. Can you make a vector out of gamma?
Gamma of t.
Gamma of t is not a vector.
Can you,
Gamma dot. This is the vector, the velocity vector of gamma, right? This is the velocity vector of gamma. So this guy is the derivative of y along the curve, okay? And by definition, yeah, I can use the exact same thing here. For any large x, I'm replacing large x by gamma dot. For any large x, I'm gonna put the corresponding gamma dot, which is little x dot, okay? So this guy is the kth component, two terms, partial yk, partial x j times x j dot plus gamma I j k x I dot y j. Maybe a summation, that's fine. can see here, look at this, partial y, partial x times x dot. What is this originally? Partial y, partial x times x dot, it's the same x. What's this? This is y dot, right? d by dt for y, k, and yk is function of x's, we write it in this form. So finally, I'm very ready now to write down the acceleration. Acceleration of a curve. Please bear with me here, you'll have some time to write. The acceleration of a curve. This will be the derivative of what? Derivative of what? Acceleration is the derivative of what?
Velocity.
Velocity along the curve. So derivative of velocity, gamma dot, along gamma. So that's fine. This is indeed, how do you write it? Nabla what? I'm differentiating the velocity along the velocity of the curve, right? And now I'm going to replace hy by little x dot. So this is xk double dot plus summation. I will just drop the summation here. xi dot xj. This is indeed the acceleration of a curve. And its tangent vector transforms from any coordinate system to any coordinate system. This first term, the double dot terms of the coordinates, does not transform under change of coordinates. Does not transform well. This is what we have seen from the example. But adding this very complicated thing makes things perfect. And I'm very ready to define the straight line. This will be our 10th word. The straight line, we give it a name in differential geometry, it's called geodesic. This is simply a straight line. And what was our definition for the straight line? What was our definition? Anybody remembers?
No accelerations along the constant.
Zero acceleration. So a geodesic on M is a curve gamma satisfying what? Zero acceleration. Nabla gamma dot. Here is your acceleration.